So I'm going to talk about chemically active sheets as models for microscale motors, not necessarily molecular, but microscale motors. And we took the inspiration from nature for these systems. And these systems have not yet been made. So this is a computational modeling talk, and the systems themselves have not been fabricated. But I wanted to show you that they exist somewhere. They exist in some space. So I'm going to draw analogies with systems in nature. Before I do that, I want to acknowledge Yushman Sen, who I have a wonderful collaboration with, and Shukong Lee, who I also enjoy collaborating with immensely. So this is actually an area that Yushman Sen discovered. So he found that if he put a patch of enzyme, if he immobilized enzymes on a surface, and then put the right reactant to start the enzymatic reaction, then the enzymatic reaction released energy, which would propel fluid flow. And because he discovered it, he could name it, and so he called that a pump. And a motor is a very similar thing, except now the surface is mobile. So it's, say, a sphere coated with enzymes. Now you add the reactant, and the sphere can move. In all those different scenarios, you have the two scenarios. The flow is chemically generated by the chemical reaction, but the flow can't do anything to the pump. It can't move it, can't change its shape. And also, when the flow hits a motor, then the motors are typically hard particles. It can't change its shape either. It can move it, but can't change its shape. So we decided to explore this other space where now the material is a soft, elastic, two-dimensional sheet. And the fun in that is now when the flow is generated chemically, the generated flow can influence the shape of the sheet. That's what you're seeing here. And then the shape of the sheet will impact the flow. So the mystery behind this, or the mechanism behind this, is Solutal buoyancy. And how many of you are familiar with Solutal buoyancy? Yeah, I didn't think so. But how many of you are familiar with thermal buoyancy? Okay, so thermal buoyancy, if you have water and you heat the bottom of a container that has the water in it, then the less dense portions of the fluid will rise upward. And if it's in a closed container, then it'll make these convective rolls. So this similar thing happens in Solutal buoyancy. So if I have an enzymatic reaction, so here's my patch, and the reactants and products have different volumes. I'm not creating or destroying mass. They just have different volumes. Then locally, I'll have a density gradient. That density gradient creates a force. That force acts on the fluid. And then that fluid will then act on these sheets. So that generated fluid not only transports the sheets, but it morphs the shape of the sheets. And this is an incredibly beautiful paper. It's really new. And this is the first example where someone actually showed that Solutal buoyancy occurs in nature. So this is a yeast colony, and they eat, and so they undergo metabolism. And so they take the reactants and convert them to products, and they generate this inward flow that I've drawn as a cartoon, and then that separates the colony. And there's great evolutionary purpose in that, because if you're going to take over the world, then you might want to spread out as far as you can. So this phenomena actually does exist. And, oh, good, these equations come out. And there are equations. It's a computational model. I'm not going to go through them. The only thing I want to emphasize is that the beauty of doing multi-scale modeling or multi-physics modeling, that you can, starting with a continuum model, incorporate molecular scale parameters. So here, the catalysis is modeled by the Michaelis-Menten equation, and those reaction rates do have information about the particular molecule that you're looking at. But quickly, one is just the Navier-Stokes equation, then the other one is the gradients in chemical concentration, and the nodes of the sheets move. So that's what all these equations are. And I was really heartened when someone said they were interested in chemo-mechanical transduction. I think you were. And chemo-mechanical transduction is just so beautiful and so completely unexplored as a method for materials design. You know, we design these monolithic things that are stationary. But using chemo-mechanical transduction, I can design gears. And so I cut this sheet, and the green one has catalase, so that's the active one. And the black one has nothing on it. It's purely passive. And now I add hydrogen peroxide to the solution. The hydrogen peroxide interacts with the catalase. It pumps up and rotates. But I put little cogs on it so that it actually moves the passive one as well. So that's the simplest kind of machine you can make are gears. And yet, here's this other beautiful paper that just came out recently. This is the first example that someone has noticed. I mean, I'm sure there might be others, where gears occur in biology, and that gears are helpful in moving objects. So this is an insect that can jump 3 feet. And the way it does it, it coordinates its hind legs very, very carefully. So it's got these biological gears that move in a synchronous behavior, and that way the 2 hind legs are just perfectly interlocked to be able to jump 3 feet. So gears are in nature too. So the other example that we were really excited about is you can take the chemical sheet, and instead of cutting it into a pattern, you can impose a chemical pattern just by localizing the enzymes in certain regions, and so that being able to put chemistry where you'd like is critically important here. And the really cool thing about catalysis, many of the cool things about catalysis, is it's reaction specific. So I have 3 different catalysts there, and it doesn't really matter what they are, but then I add the appropriate reactant, and I only initiate catalysis on the green part, because this is hydrogen peroxide, and that only initiates catalase. And then I have another catalyst, and I add reactant, and that only initiates the reaction on the red part. And I can play the trick with coating the walls, too. So I can use the reactions on the walls as well to drive this structure formation. Why this is cool is because there really aren't very many examples where one material gives you multiple structures. And all you have to do is change the chemistry in the solution. So that one was a chemically active sheet, and now we wanted to see what happens when we combine chemically active sheets or chemically passive sheets and pumps. Remember, pumps were immobilized on the surface. They can't move, but they generate a catalytic reaction, and that generates fluid flow. Sorry, what? Okay, so I'm already pretty much done with this. And by coupling the behavior of the pumps and both the catalyst. Oh, hello. Came just in time. So coupling the fluid that's generated by the pump, you can make these passive sheets undergo this oscillatory behavior. And then these are active sheets and an active pump. And I'll quickly point out that there is a scenario in nature. It's the sex life of this tree frog. You can ask me about it later. It's a really fascinating thing. And then we made self-intertwining materials. So these are materials that interknit. And these are passive sheets. And the patch is where the catalyst is located. And we did more of these sheets, and you can mimic a weaving pattern. So you can have sort of a self-weaving material. And then in the final one, there's not really a mimic in biology, but I just love this painting by Matisse. And I wanted to show, could I make something that looked like a painting, sort of mimicking biology? And the answer is yes, if you squint. So, here are the arms are coming together, and then the bodies are coming together. And if you look at the shape of the bodies and look at the shape of the sheets, they're really quite identical. He's a very good painter. But the point of this was that there are design rules. It's not magic. You can sort of learn how to tailor the system by tailoring chemistry to tailor the flow and tailor the sheet. Thank you.
So as an ignorant person, I know that these rules are going to change as you make things get smaller and smaller.
Yes, I'm so sorry. I should
Yeah.
have said that. That's the thing I
So
always leave out.
Yeah. So can you give us any insights about that? Or,
Yeah. So these sheets are on the micron, nanometer to micron to millimeter scale. The chemistry is on the nanometer scale, and so it will scale. But that's the ballpark we've been playing in, sort of the micron to the millimeter scale. I actually don't want to play in the nanometer scale. I want to be able to visualize these things. And the idea of the nanoscale, the beauty to me is coupling the nanoscale to the micro to the macro. And that's coupled here because you have the chemical reaction on the nanoscale. It's generating a microscale fluid flow, which is then causing a macroscopic change in the sheet.
And can we have Svet come up already?
You mentioned change in volume of the reactants in the products. What about chemical potentials? Are you simplifying this for us, or?
I'm not simplifying it for you. There's a force term in the Navier-Stokes equation that's proportional to the local variations in density. And the local variations in density are caused by the fact that the reactants and molecules can have different volumes and therefore different masses. But it's that you have a very nice localized gradient in density, and that's what drives the fluid flow because it's a force term acting on the fluid.
Okay.